let's try this again. This is the third time I've tried this video, starting at slide 48. I'm having trouble with Snagit. But anyway, here's a cross section of the retina. The choroid out here, the pigmented layer right here, and then there are three layers of cells in neural retina: the photoreceptor cells, the rods and the cones, the bipolar cells that the photoreceptors synapse upon, and then the ganglion cells moving from the outside in that the bipolar cells synapse upon. And in between these layers are cells called amacrine cells and horizontal cells. And they do something called peripheral inhibition, which we'll get to later on when we get to visual processing more. Now, the photoreceptors and the bipolar cells are not excitatory. They do not generate action potentials, just local potentials. But the ganglion cells do, and so action potentials are generated in their axons, which make up the optic nerve. But look at the arrangement of these cells. This is really interesting and frankly bizarre. The outer tips of the photoreceptors are embedded in the pigmented layer, and they are pointing away from the light. The light comes in this direction through all the wiring before it hits the photoreceptors. In other words, the retina is designed backwards. Why? I don't know. Nobody knows. That's just the way it evolved. And the information flow has to go back out this way to form the optic nerve to go back into the brain through the retina. And that's where the optic disc is, and that's where the blind spot is. Because all the axons have to coalesce to form the optic nerve, and you can't put photoreceptors there. Right? And so there's a flow in a retina because of that, because it's designed backwards. And why is it you don't see a black spot out in your visual field? It's because your brain fills that in. It just makes believe that what's in the blank spot is the same on both sides of the blank spot. Okay, that's called the optic disc, where the blind spot is. The fovea centralis is in the middle of what's called the macula lutea, and it's the greatest area of visual acuity. If you focus on something in the distance, that's where the light hits. And here is a photomicrograph of this with the chorea out here, the pigmented layer, the rods and cones, the bipolars, and the ganglion cells. So neural components of retina, three layers: photoreceptors, rods, and cones, which are responsible for what's called scotopic and photopic vision. Scotopic is under low light, and that's using rods. Photopic is under high light, and that's using cones. And then they synapse upon the bipolar cells, the ganglion cells not in layers, horizontal and amacrine, and then the visual pigments that are combinations of a vitamin A derivative and a protein. In rods, it's called rhodopsin. It's very sensitive to light, but no color. That's why you can't really see colors at night. Photopsin, this is in cones, it's much less sensitive to light, but you get color with it, and you get more accurate vision with it as well. Move to focusing now with the lens. Lens is held in place by suspensory ligaments. They're attached to the lens, and the other side is attached to the ciliary body. The default state is the ciliary muscle is relaxed, and that's when you're looking at a distance, right? And the ciliary muscle relaxes, it exerts tension on the suspensory ligaments and stretches the lens so it's thinner. This is, again, something bizarre when it comes to muscle. No muscle does this except for the ciliary muscle. It's the only example of a muscle that exerts tension when it is relaxed. And so this is one of the internal eye muscles that are not under your control. The muscles that control the iris and the muscles that control the stretching of the lens. The other muscles are the external eye muscles, and they're under voluntary control. ciliary muscle is contracted by parasympathetic stimulation. So that so that uh, so that causes your the the tension on the suspensory ligaments to decrease. The lens goes back into a thicker shape, and then it allows you to look at near vision. So it reduces tension on suspensory ligaments because when spherical, light bends more for near vision. I'll show you this figure of this in the next slide. This is called accommodation. To the left, lens shape for distant vision, ciliary muscle relaxed, suspensory ligaments taut, lens flattened, light not bend as much, and it focuses back on the back of the retina. But for near vision, you have to relax the ciliary muscle. This is a parasympathetic reflex. The suspensory ligaments are relaxed, and the lens, which is like a stretched rubber band in the for distant vision, is now contracts and is thicker and bends light more for near vision. Now my eyes cannot do this anymore because I had cataracts in both eyes. My lenses were removed and replaced with plastic, and the old type of plastic could not accommodate. So I have to use reading glasses now. Slide 52, back to the eye cavities, the anterior cavity with two chambers and a sclerovenous sinus which collects aqueous humor in the posterior chamber as a ciliary process that produces aqueous humor. Posterior cavity has a different kind of humor. It's called vitreous humor. It's jelly-like stuff and does not circulate. Here's a figure of the lens, and to the left is the posterior chamber, the suspensory ligaments, the ciliary process, the iris, and the flow of aqueous humor from the anterior chamber of the anterior cavity through the pupil to the in the posterior chamber of the anterior cavity, through the pupil to the anterior chamber of the anterior cavity, and collected by the sclerovenous sinus, which used to be called, in my day, the canals of Schlemm. And this circulation happens 24/7 all the time, and the problem is sometimes these sclerovenous sinuses get clogged up for some reason, do not allow the aqueous humor to be reabsorbed. It builds up, causes pressure in the eye, and this is glaucoma, which is completely preventable, but yet is still the most common cause of blindness.